Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Okay, folks, thank you for joining us for the last colloquium of the fall quarter. I realize it's a busy time of year. It's great to welcome back Oren Etzioni. Oren, you all know him well. He overcame his humble origins as the child of a world-renowned sociologist and a graduate of Harvard University to become one of the leaders in artificial intelligence. Spent most of his career in our department after getting his degree from Carnegie Mellon, and just this year left to become the CEO of the Allen Institute for Artificial Intelligence. And our hope is that AI2 does for artificial intelligence in Seattle what the Allen Institute for Brain Science has done for neuroscience and brain science, which is to bring it to an entirely different level and make this part of the world the center of what's going on. So, Oren, thanks so much for coming back today to join us.
Thanks, Ed. I love what I do at AI2, but I have to say I also miss the department, miss teaching, so it's a real pleasure to be here. And in fact, speaking of teaching, we're going to have a little pop quiz, so if you can take out your pencil. No, just kidding. I'm here to talk about AI and AI2, and I've got lots of stuff, so I'll go quickly. I'll take some questions, but I might defer technical details for later. This is the view from our deck on AI2, just 5 minutes by bike from here, so I invite all of you to come, and some of you to stay. Luis asked me if this is a job interview, and I told him, no, we're not hiring in architecture, but we are hiring in other areas. So to be frank with you, part of this is an infomercial for AI2. Okay, let's get into it. So this starts, one way to think about it, why did I get involved with these things? Starts with this quote: in order to be intelligent, computers must understand. It's one thing to feed the tale of two cities into a computer. It's another thing to have the computer understand what's being said. And this is the kind of thing that I say if somebody from the popular press calls me to talk about AI, that's the sort of thing I would say is beyond the state of the art, is what we ought to be working on. The impressive thing about this statement is it was said by Paul Allen back in 1977. So Paul is somebody who really gets it. And as we've gotten all excited about cool hacks of various sorts, he's somebody who's kept his eye on the prize and said, okay, but how do we get to make progress on the original goals of AI? And so he founded AI2 with a mission of contributing to the world through high-impact research and engineering, with emphasis on natural language processing and more recently vision, and tying those to reasoning and knowledge representation. Quickly, here's our chronology and geography. We're actually launched in January. By this fall, we've reached a team of 30 people, mostly technical, and we had 12 interns. Our goal is to be a team of 50 people by the end of 2015. So again, you can do the math. We're hiring. As I mentioned, right, you can see we're right off the Burke-Gilman Trail here, right on the water. It's a really fun space, and love to have visitors and have you stay. So the next question is hiring. As I mentioned, big emphasis for us. It's incredibly competitive, particularly in Seattle, where from Alibaba and Apple to Zillow and Zulily, everybody's hiring researchers, machine learning folks, AI folks, et cetera. How are we going to succeed? And I went back to, this is Herb Simon, one of the most illustrated, probably the most illustrious computer scientists. He won a Turing Award and a Nobel Prize, and that's just before getting out of bed. So he was a professor of mine in grad school, and he always liked to say, in order to do good research, you have to have a secret weapon. And the notion here is not secret weapon as in something secretive, but secret weapon as in some kind of competitive edge. So it became very clear to me as I was founding or developing the plan for AI2 that AI2 also needs a secret weapon if we're going to succeed in this highly competitive climate. And so I want to reveal to you for the first time AI2's secret weapon, and that's computer science. So I thought that if I can build on my affiliation with computer science, the close relationship, the geographical proximity, if we have this kind of elegance of people coming from the Paul G. Allen Computer Science Center to the Allen Institute of AI, if we get that flow going, maybe even back and forth, that would be tremendous. And I'm glad to report that that's already started. So Ed is on our board. Dan is on our scientific advisory board. Hannah and I and Ali have been collaborating. Hannah and Ali won an ADI award. Actually, we'll save the applause because Jeff and Luke also won one. So that's a really a tremendous achievement. And again, I can assure you, I had nothing to do with this. It was an independent panel. It's another arm. It's the Paul Allen Foundation. But they're very richly deserving. It was incredibly competitive. Over 100 proposals submitted from all over the place. We also had a whole bunch of interns last summer, including 8 from UW-CSE. You'll recognize some of the folks in this picture. And again, summer at AI2 is lots of fun. And then if you look at our org chart, I highlighted in purple the folks who have UW-CSE affiliation or a degree. Ali is joining us to help on a small part-time basis to help lead our vision efforts. We have a number of graduates from CSE. About a third come from CSE, and we want more. Okay, end of the first part of my infomercial. Let's go to the talk. What I want to talk about today is the limits of what's called the big data paradigm. I'll explain what that means. I think everybody knows what big data is. I'll talk about what the limits are. And I want to argue that AI needs knowledge, reasoning, and explanation. Depending on who you are, that might be completely obvious, of course, what were you thinking? Or that's ridiculous, you're crazy. And I like to make statements that are roughly evenly split among 2 completely opposing points of view. And I'll tell you why I think one side is right now the other. We'll talk about knowledge bases and the extent to which they're what I like to say fact-rich but knowledge-poor. I'll talk about reading the web, which is a work that I and Dan Weld and others did over 10 years or so at UW, and why that's not fully solving the problem. And I'll talk about our ambitions for machine reading as forming automatic theories for people as the next step. And I'll again end with the specific projects at AI2. If people have good questions, I actually have here a t-shirt. You ask a good question, you get a t-shirt. You can save them to the end or not. I think I have a good supply. Unfortunately, Pedro is not the audience. I was all set for Pedro to ask a question, which, as you know, he does from time to time, and then to tell him, not a good question, no t-shirt for you. But damn. Anyway, it's good to play to a home crowd. What can I say? So we're all aware of the big data tidal wave, the tremendous success that's very real that's been achieved here. I'm the guy here on the side looking at this and thinking, okay, this is pretty cool, but what's going to happen to these people next? Specifically, or mixing the metaphors, what are the limits of this paradigm? How far does it go? And I should point out that the critique I'm going to develop here quickly applies to descriptive methods, generative methods, deep learning, SVMs, the works. It's all about these methods that do some kind of classification and prediction. And here's the problem, and this is a simple example from the New York Times to illustrate this. And so there was a New York Times article, and it was based on a paper by Tanley and Peng from Cornell that appeared in ACL 14. And they said, let's look at 2 tweets issued actually by Al Gore about the same article in The Atlantic, and let's ask which of those is more likely to be retweeted. That's the type of thing we can do with big data, right? We can model this whole situation as a set of features, as a vector, and then predict which one's more likely to be retweeted. So he said about the same article, 40% of smartphone users connect to the internet before leaving bed. That's the top tweet. And then the bottom one is the cybercrime market is now greater than the annual global market for marijuana, cocaine, and heroin. So show of hands, how many people think that the top tweet about 40% of the smartphone users will get retweeted more? And how many people think it's the bottom? Okay, unclear. And that's the really cool thing about these statistical models. It predicted successfully that the top one was actually retweeted about 3 times as often. Okay? So that's a pretty nice result. But then the author of this article asked the question, what about creating tweets in the first place? Okay, again, not rocket science, but a substantially more creative act than saying which tweet is going to be more popular. Well, we don't have any programs that do this in any reasonable way. right? Certainly not one that reads an article and takes out a concise, pithy overview of what's in there and creates that as a reasonable tweet that people would be interested in. So the point being, this illustrates just how incredibly limited this paradigm is. Classification and prediction, there's a lot more to intelligence than that. And that's really my point. To build intelligent systems, we need just a much more sophisticated process, a lot more like kids playing with Lego. Constructive, it's multi-layered, it's recursive in the sense that once you build a layer, then you build on top of it, you experiment, you try different things. Frankly, it's a lot more fun than just making binary predictions about whatever. It's really a process where you have data, you form theories, you reason over these theories. That reasoning gets you to look at new data, and this keeps going. Another analogy to get the intuition across, think of in thinking fast and slow, system one, which is the fast associative thing, but it's also biased and error prone. That's a lot like what big data can do, classify and make distinctions, compared to system two, which is more deliberative, explicit, it's more reliable, a lot more like a CSE faculty member. And at least sometimes. And that's what we need in these systems. So I'm going to repurpose a quote here from another one of my old professors, Alan Newell. He said, you can't play 20 questions with nature and win. The point is that if you're reduced to making binary distinctions, you can't get that far with that. Now, of course, conceptually, I see Anna in the audience. Conceptually, of course, you can reduce everything to bits. So the point isn't, can you code everything in zeros and ones? Sure you can. It's just not practical as a way of building things, right? We don't want to program in binary. I have lots more examples. I'll just give you one more. Let's take chess playing machines. Chess playing would seem a priori to be a great thing to do classification over, because the basic chess playing problem, or any game playing problem, is you have a board position and you have a set of moves to choose from, and you just need to classify the board position into one of an average of 30 buckets, right? Each bucket representing a move. What could be easier? You also need labeled data. Well, guess what? By being able to run games to the computer, you can have billions, if not trillions, of labeled data instances, right? Here's the position, here's the move, and did I win the game or not? So it would seem trivial that with deep learning or big data or whatever your favorite flavor is, you should be able to play chess that way, except that we don't. So Deep Blue was looking at billions of positions, analyzing billions of possibilities before making a move. Even human grandmasters, which have an amazing capacity for classification and categorization using our advanced visual cortex, if you take two grandmasters and you put one who has to move instantly, right, and then is distracted, and one who actually gets to think for 5-10 minutes about the game, the one who can think will always win, right? Because you need analysis, you need reasoning to do this sort of stuff. So this is not a proof, this is argument by example, but this is my claim why classification only goes so far. We need to build on it to come up with better systems. And my last example, and one that I'm going to go through in more detail, is natural language understanding. So a great illustration of where we need much more sophisticated systems. Let me again start with a simple example. This is the Winograd Schema challenge, popularized by Terry Winograd in the 70s and rediscovered and emphasized by Levesque recently. Let's look at an example. These schemas are sentences where you change one word and something changes radically. So the large ball crashed right through the table because it was made of styrofoam. A person instantly realized that it here refers to the... Thank you. You know, you can get the professor out of the university, you can't get the professoring out of the professor. If you just change the word styrofoam to steel, so you change one word in this sentence, now the binding of it flips, right? So the large ball crashed right through the table because it was made of steel. It here refers to the ball. Now the reason I like this particular Winograd schema, the schemas always have this form. You change one word and the binding of something changes. But the key is, to make these decisions, you have to know about materials. Styrofoam, wood, steel, what have you. You have to know about furniture. You have to know about basic verbs in English. If you don't have that really vast array of knowledge, there is no way you can do the most basic natural language understanding task. This is what's called pronoun resolution. You can't do it if you don't have a vast amount of knowledge. So the claim, and hopefully I've proven this to you by example, is world knowledge is necessary for NLP. So, and again, this is an old, we've known this in AI for a long time. We just found it convenient to forget about it while we pursued other things. So the next question I asked is, well, before we think about machine learning and how do we obtain these knowledge, maybe current KBs have it. Knowledge bases, there's some very famous ones that have been constructed manually, and they're really quite impressive. So I started with the following thought experiment. I asked myself, how much do I know, or how much do you know about apples? And I submit to you that if you just, again, took out that pencil I mentioned earlier and scribbled a few facts, within a couple of minutes you could get easily 20 non-trivial facts about apple, from that it has edible, fruit are edible, they consist mostly of water, they ripen on trees, et cetera, et cetera. This is common sense knowledge. If I allow you to use inheritance, and you can also include facts about fruit and about food, the sky's the limit, right? You can write a lot of stuff about that. So I said, let's take a knowledge tour. Let's go to different famous knowledge bases and see what do they know about apples. Well, I started with Google's famous knowledge graph, hundreds of millions of facts, hundreds of millions of dollars gone into it. I typed Apple into Google. It sent me to the Apple store in the uVillage. They're incented to do that, so that's not quite fair. So I said, okay, let's do Apple the fruit. I asked it about Apple the fruit. It gives me an impressive number of nutritional facts from some table that it's ingested, but really doesn't tell me the basic things I'd like to know about apples if I want to understand natural language, like that it's an edible fruit, et cetera. I went to Wolfram Alpha. Turns out Wolfram Alpha has been reading from the same nutritional database, or most likely they licensed a similar one. Same thing happens. I get infinite amount of nutritional facts that are largely irrelevant. The basic common sense facts are nowhere to be found. I went to Psych, which is a project, I think most of you, how many people have heard of Psych? Okay, so there's a few people who haven't. It's a project that's been going on for 30 years for manually entering knowledge into a computer. They've spent upwards of $100 million. It's been a resounding failure, but they still go around and say that they're a success. So I went to the open version of Psych, asked it, do you know about apples? It did know that apple is an edible fruit, and that's about all it would tell me. I went to ConceptNet, which is a famous project out of MIT that relies on volunteers. It was an early example of crowdsourcing. And it turns out it does know a fair number of things about Apple, but it doesn't distinguish at all between apples being green and apples being computers and apple being an antonym to orange. It's pretty much of a mess. So that didn't do it. Here's the bottom line. First of all, transparency is great. Okay, I've been able to go to all these sites very quickly. I'll show you a bunch more in a second. And they put their data on the web, and we can see that. Number two, this is not about apples. I tried oranges. I tried jellyfish. This is about common sense knowledge. And the bottom line about common sense knowledge is these famous manually created knowledge bases have major gaping holes in them, even in terms of their basic factual knowledge. So then I said, okay, what about obtaining knowledge by reading the web? These manual knowledge bases aren't going to cut it. What about the work that Dan and I have been doing for a long time? And this picture is stolen from a major DARPA initiative that's supporting it. The idea of machine reading is to take text that's on the web and elsewhere and translate it into a formal knowledge base that the machine can use. And the basic idea is to use a technique called information extraction, or IE. IE implements a function from a sentence like Edison, by all accounts, was the inventor of the light bulb, to something more formal like invented Edison light bulb, and maybe an associated probability or confidence. That's how this works. Typically, this requires you to pre-specify the relations or concepts of interest and to give hand-labeled training examples. And there's been a lot of work to weaken these assumptions. Let me give you an example of this, and this is from Tom Mitchell's NELL system, Never Ending Language Learner. This is a system that's been running for about 4 years now at CMU. It's one of the leaders in the field, and again, he puts up the knowledge that NELL learns on the web. So I went to NELL, and I chose really at random the relation haswife. And what it has is various lexical patterns, basically combinations of words and strings that lead you to indicate that X's wife is Y. And to enlarge it, I took the top patterns, and you see that it learns things like X is a bad influence on Y. That means that they're married. X had a child through Y. X is abusive to Y, X, et cetera, et cetera. And I found this quite surprising, so I dug in a little bit more why these are the patterns. It turns out that because NELL is autonomous, it's developed an unhealthy obsession with Angelina Jolie. And that's where a lot of this comes from. But that's an aside. Then I went and asked NELL about Apple. You can't see this, but it was pretty slim pickings. In fairness to NELL, it's not focused on common sense nouns. It's more focused on proper nouns. So I asked it about Obama, and it did better about Obama. NELL knows that Obama's a politician, that he's male, that he graduated from Harvard. But still, for a system that's been learning from the web for 4 years, you got about 6 facts that it knows with certainty, compared to how many would you be able to spout about Obama at any given time. So again, answer quite, that's not the answer. Next, I went to open information extraction, which is the set of techniques that we were working on here for many years. And you'll see that my research is not spared from this criticism. We don't have the answer either. The open information extraction, the idea is to leverage regularities in language to avoid having to have hand-labeled examples and pre-specified relations. We rely more on characteristics of language, like relationships are often expressed in verbs, they exhibit a simple syntactic form, and we use the redundancy of the web. One of our mottos was no sentence left behind, which means that we were able to extract information from any sentence, or at least any sentence in English. By now, OpenAI has been implemented for at least 5 other languages, including Chinese. Anyway, I asked the demo, which miraculously is still running on the UW servers, what do you know about Apple? And it asked me, do you mean Apple the company or Apple the fruit? Which I thought was good. We said Apple the fruit. And you find that it does know a bunch of stuff about apples. I was pleased that they grow on trees, that they contain pectin. They're a good source of dietary fiber. They fall from trees. That's pretty good. However, still those basic facts were not present. Basically what I found is that OpenAI suffers from attention deficit disorder. It's not surprising. It operates one sentence at a time, and it's been run over 1 billion pages, one sentence at a time. It knows all kinds of completely random stuff. Imagine a kid who read 1 billion pages on the web and said, okay, now I'm ready to go to high school. I don't think so. So pretty limited. Another direction that we've looked at, which is a lot of fun. So this is work with Ferste, who I see here, and Santosh, who's at AI2, and Ali. This was recently submitted to CVPR. The basic idea is to build image detectors and to put them in concert in order to be able to answer these tuple-based questions like, do dogs eat ice cream? I didn't ask the system about apples specifically. And you see that for questions like that, if you ask it, do snakes lay eggs? OpenAI knows this information, MIT's ConceptNet doesn't, and Visual AI does as well. If you look at dogs eat ice cream, there's plenty of things that are visually expressed. And so the basic idea of Viz AI is that we can get information from pictures if we can't get it from text. And that's a pretty exciting research direction. Mean average precision here of these triples is 0.54, which is not stellar, but this is the first paper along these lines, and I know they're working on improving that over time. So everything I've said so far is about facts, but the truth is that even if you have a comprehensive collection of facts, that's not good enough, okay? If you want to remember, I talked about theory formation. You also need rules, reasoning, explanations. Basically, a theory is greater than the sum of its facts, which is a concise way of saying that I don't know how to formally characterize theories, but it's something more than a bunch of facts. So what are we doing in AI2? Now to cut to the chase, we're trying to do high-impact long-term research, and we're focused on taking textbooks and scholarly papers and mapping them into theories that you can reason over. As simple as that. And that's a major step forward, because you have to remember that my survey of the state of the art, both manual and automated, showed that we can't even get comprehensive collections of atomic facts. And we're here saying we don't want just facts, we want facts coupled with rules in a way that allows you to draw conclusions. So where are we at with that? I'm going to tell you our basic scientific methodology, and then I'll show you some examples of projects that we're doing. First of all, again, as we've all known, in the field, knowledge and reasoning is necessary for AI. The whole deep learning, big data thing has ignored that, but most people would agree that's true. This knowledge has to be acquired highly automatically. So we've had lessons from Psych and other projects. It just doesn't scale to try and do it by hand. So we assume that. We believe, and this is a lesson from Watson, that we need crisp benchmarks to track this. It's just all too easy to do some experiment and then write some paper, invent some metric, and say, look, on my strange metric, whether it's called blue or rouge or some other thing, I'm doing great. I have a happy curve. The paper is publishable. I've written lots of those papers. So have you. I see the people trying to slink away from my piercing gaze. They're really not that great. So what we did is we defined the target ahead of time, and we said, let's do it. And I'll talk to you about what that exact target is. And then what we posit is that these large bodies of high-quality knowledge can be acquired from text. That's this machine reading idea that we're continuing to push on, but also from images and diagrams, and down the road even videos. And that's an incredibly hard problem, which is why Ali is there. At least 20% of Ali's time. I think we've got this licked. One of the things that we found out as we've been working to acquire knowledge is even if the knowledge is seemingly very simple, we take a science textbook for fourth graders, the knowledge that we're actually able to acquire from language is quite noisy and incomplete. And so it seems like one of the things we really need is robust reasoning under uncertainty. Pedro, where are you? So this would be music to Pedro's ears. But it's OK. I'll show you in a second how Pedro's techniques fail miserably at this task. OK, so again, to put this in context for non-AI people, let's contrast what we're doing with Watson and Psych, prominent efforts. So Psych, I've beat up on enough. It's manually engineered. It has very heavy-duty deductive machinery. It's an awesome system, except for the fact that it doesn't work. Watson is a very impressive system in that it did work, but it worked for a very narrow task. It was highly optimized for Jeopardy. In several years, IBM has not been able to shift that infrastructure to different tasks, with the exception of creating barbecue sauce. So there is an IBM-branded Watson barbecue sauce, but that's about it. So AI2, compared to these two approaches, has two key virtues. First of all, we haven't tried anything yet, so you can't accuse us of failing. We're relatively new kid on the block. And secondly, our philosophy is to collaborate and publish and open source our efforts. So really, if there are failures, they're your fault. So no, I'm joking. We've actually had some successes, but the point is, I don't know that we have the right answers, but at least we're not repeating mistakes that were made earlier, both methodologically and in terms of our approach. We are trying to build a library of knowledge bases and ontologies. We are trying to do tractable probabilistic inference on top of those, and to do it in a lighter weight way than Psych. Yes?
In hindsight, is there something that makes Jeopardy easy? Because on the surface, and certainly at the time, Jeopardy seemed really hard.
Good question. So the question is, to repeat for the people watching the webcast, is there anything that makes Jeopardy easy? Because it's extremely hard with the convoluted questions and so on. The short answer is there are things that make Jeopardy easy. They did very careful analysis of the question types. They used databases to farm off a bunch of questions. Nevertheless, it's a very impressive achievement. So it's not general purpose English, but it is a very hard task. The real problem is, what do you learn from that, and how do you generalize the architecture that was used? And that would take me to another talk to explain why that's failed. But it's tricky. OK. So let me show you some of the results that we've had, and I'll touch on these lightly and report to papers. The first one, which I really love, is work that we did on geometry questions for 9th graders. And this is work that we did collaboratively with Min Sao. Is he? He's too busy working on our next paper, and with Ali and Hannah. So it's a collaboration of computer science and AI2. You see the color coding on the authors. Red is for our Korean authors. Purple is for our Persian authors. And green is for the Israelis. This is part of a growing trend of collaboration between Korean, Iranian, and Israeli scientists in the field of artificial intelligence. It really is growing because we hope to write more papers together. Anyway, here's the problem that we solve. Look at these types of questions, right? You may remember this from 9th grade. The point is, if you look at these, and if you just have the diagram, you can't solve the question, right? Not enough information. Turns out that for most of these, if you just have the text, you can't solve the question either. So the first problem that we looked at is how do we take both and compute the appropriate alignment between the diagram and the text? And remember that the diagram is coming into the computer as just a set of pixels, and the text is raw text. We don't deal with OCR level issues, but other than that, it's just as is. Well, we were able to solve this problem, and the idea is you can see right, secant AB is in red there in the text, and it corresponds to the line. We have circle O in brown, corresponds to the circle, et cetera, and it can actually even start to infer certain things based on the length of these. So we've done this alignment. This was modeled as an optimization problem, so we took into account that we want to maximize the pixel coverage of our model. We want it to be as coherent as possible, right? We want things that intersect at corners or at points to be recorded correctly, for example, at point D. And we also wanted to maximize things relative to alignment with the text, right? If you come up with some shape, but it's not mentioned in the text, there's a penalty for that in the model. Only problem is that this optimization requires 2 to the L operations, where L is the number of visual primitives here, lines or arcs. And so it's intractable. And we observed that the function is actually submodular. And by we, I mean Ali did. I'm not smart enough to do that. But I always wanted to write a paper with the word submodular in it, right? Why should Jeff Bilmes have all the fun? And so, I'm sorry? And so we have an approximation algorithm that's close to optimal, and empirically we get actually fantastic results, right? Our F1 scores, the light blue is ours, and it's approaching 95%, which is very strong results. And now we're building a geometry theorem prover that takes the text, takes the diagrams, takes the alignment, actually able to solve the problems. And this will be the first system of its kind that's able to solve 9th grade geometry problems as is. And the first paper is in IIII 14 if you want to see it. I don't have time for the demo, but there's a demo too. Okay, let me tell you, that was kind of a little bit of toe in the water, geometry, simple geometry problem, simple alignment. Let's talk about Aristo, which is our major project trying to do science. So what we're doing here is we're taking textbooks and mapping them to theories, as I said, and we're testing Aristo on unseen standardized tests. I mentioned geometry. We've also done some work on arithmetic, but science is a huge focus for us. Can you take a 4th grade science test, let's say the Regents test from New York, and test a program on it? And the challenges here are natural language processing, reasoning to solve the problem, and also vision, because these things are full of diagrams. These tests, more than 40% of the questions have diagrams, and most of these diagrams are actually essential to solving the problem. So we started with easy diagrams in geometry. These diagrams, they've got plants, they've got the water cycle. They're incredibly challenging to address. So here's what these questions look like. Which force caused the bicycle to slow down when the brakes are used? Is it friction, electricity, gravity, or magnetism? Again, the problems are pretty easy for a person, but you need common sense knowledge. You need to understand the question. You need to make sense of the answers to solve this sort of thing. Let me show you an example of what Aristo is able to do today. And I should tell you that our result is on the non-diagram multiple choice subset of the test. We were able to achieve 66% so far. And again, there is no other system in the world that can do that. We put our data on the website. It's like that Duracell commercial where the guy's got the battery on his shoulders like, I dare you to knock it off. I dare anybody in the audience, and even teams of you, to defeat us. We'll think of an appropriate prize. Okay, let me kind of give you a sense of how it works in Aristo today. It's not super impressive yet. Here's another question. Which example describes an organism taking in nutrients? Dog bearing a bone, a girl eating an apple, et cetera, et cetera. So what we do is we take the question and each of the answers, we transform it to a hypothesis in declarative form. So if we take B, we say a girl eating an apple is an example of an organism taking in nutrients. And we try to prove that. We have a question interpreter that maps that to a more formal representation. And we say, okay, we know that we have a girl eating an apple. We know from WordNet that a girl is a person, which is an animal, so we can conclude that an animal is eating something. we have a rule that was extracted from the Barron Study Guide automatically that says animals must eat to get nutrients. We're able to express that rule in a, I would call it semi-formal representation that basically says that when you eat, the effect of that is you get nutrients from the food. And then we're able to conclude from that that an animal is an organism, and an organism is getting a nutrient. Again, WordNet tells us that get and take in are roughly synonymous. And so we're able to conclude that if you start with a girl eating an apple, you can roughly conclude that an organism is taking in the nutrients, and that's a correct answer, or at least with some probability. I've glossed over an enormous amount of details. But you see that the reasoning has somewhat of a sequential nature. It has large lexical components, and also it can easily be wrong. So it's a major problem. So really the question is, okay, we've got these results, but we want to go from 66% to 90-something%. How do we do that? And you really have to step back and say, so what's the reasoning method we're going to use? Deductive reasoning turns out to be too restrictive for this. Let me give you a couple of simple examples. We'll see something like the phrase that something fell down. And we want to conclude, well, it fell down to the ground. Okay, that does not follow deductively. It's not always true. But you need these kind of slippages to draw conclusions from, to apply the things you learn from the textbook to particular questions. And the questioners expect kids to have the kind of common sense that allows them to see that that makes sense. Deductive reasoning doesn't do it. Here's another example. We know that dogs breathe through their mouth. Can we conclude that animals breathe through their mouth? Well, again, that's not always true deductively, but often that's a reasonable something to jump to in the context of these tests. Deduction ain't going to cut it. Sorry, Doug. That's the psych guy. So how about shallow text alignment? Shallow text alignment is the set of techniques that gave us things like Google, like machine translation, information retrieval, all that good stuff. It turns out that, again, it falls short, and here's a simple illustration. Let's say I know from the text that something turns a liquid into a solid. It does not follow that that turns a solid into a liquid. But if you do what's called shallow text alignment, which you use what's called a bag of words model, you basically take the sentence, convert it into a set of words. From a set point of view, ignoring order and relationships, those are equivalent sets, right? So again, we can't just rely on shallow alignment. We've worked with people, and those methods work okay, but they asymptote way too low for our purposes. A sentence is not just a set of words. So let's do probabilistic reasoning, right? Let's go to Pedro. Well, I was shocked by how difficult this is. This seemed to make a lot of sense to us. These methods, Markov logic networks, other variants, are very, very popular in AI today. Turns out that there's two problems, and they're both terrible. The first one is mapping text to Markov logic networks is incredibly challenging. And I'll just give you one very simple example. Let's take a sentence like, people breathe air. Okay? You can't express that deductively, right? What if the person is dead? It turns out you can't express it probabilistically very easily. The probability calculus doesn't help you to resolve certain things. So is this all people? Is this most people? Is this at all times? Some of the times when we say air, is that a single air molecule? Is that all air? What's the temporal dimension of the statements? It'll say in the textbook, people breathe air. It'll expect the child to take that, make sense of it, and reason, okay, and answer questions. But these technologies can't do it. It's not clear how to map a sentence like that into a formal language. That's been a huge problem for us. Another problem is these methods are absurdly intractable in the sense that I take a single rule that I extracted from the textbook and I model it in MLNs, and I get a network, I get a graph that has 10 to the 10 nodes. And I could not believe, I just could not believe that this was true when they told me this. So I sat with Ashish Sabharwal, and he was Paul Beam's student, so it's got to be right. And he explained to me why this is the case. And I, in a tremendous feat of magic, and this is the most technical part of my talk, I'm going to walk you through, at least to give you the intuitions of why this happens. The state-of-the-art probabilistic methods take a sentence of text, right, that's this big, and translate it into a graph with 10 to the 10 nodes, right? Unbelievable. But this is what happens. So the example here is growing thicker fur in the winter helps some animals to stay warm. Seems reasonable. If we use a first order representation of this, this is what it looks like. It has a universally quantified antecedent and an existentially quantified consequent. Basically, the is-a statements bind variables to various strings we saw in the sentence. The interesting relational statements are in bold. So the agent of grow is an animal, the object of grow is fur, et cetera, et cetera. And then based on that, we can conclude that growing enables some animals to stay warm effectively. Now what's interesting is when you take a rule like this first order rule and you put it into an MLN, you get a huge blow up. Why is that? Here's the formula of what happens when MLN encodes K science rules. But even if K here is 1, we have something of the form D to the V, where V is the number of variables in the rule, and D is their domain size. The domain size in the rules we find from our 4th grade textbook tends to be around 10. Those of you familiar with MLN say, that's not a problem, right? We have often domains of thousands or more. But these 10 turns out to not have symmetry or exchangeability applying to them. So these are 10 genuine constants you have to enumerate over when you're grounding the network. And likewise, the number of variables for the rule turns out to be about 10. And that's about 3 times more than the typical hand-coded rules that people use. The net effect of this is that when you plug these numbers in, you see a graph where on the x-axis you have the number of science rules. And on the y-axis you have the size of the network in scientific notation. It's in scientific notation because Ashish did this graph. And these are massive. For a single rule, we're getting 10 to the 10. If we get to 10 rules, it's ridiculous, okay? So this methodology, at least out of the box, just is inconceivably intractable. Sorry, Pedro. So here's our major scientific challenge for next year. And again, we're operating, I like to say that we're a combination of a university and a startup, meaning that we're tackling fundamental questions, but we're trying to move fast. So we're going to solve this one way or another next year. We're going to develop a novel reasoning method that is scalable, robust, and supports an expressive representation that allows us to take rules extracted from text, plug them directly into this machinery, and achieve our goals in terms of solving the test. And if you want to know how we're going to do that, I'll have you talk to Ashish. Okay, so now I just have a little bit more time, and I want to describe to you our second project. And really, the main takeaway from this one is we're working on some of the toughest problems in AI in terms of acquisition of common sense knowledge with text and layering reasoning on top of it. And I'm a little bit tongue-in-cheek about we're going to solve this. I think we're going to make progress. This project I like to call the Da Vinci Project, and the observation here is that there are no Renaissance men or women anymore, okay? There are so many scientific papers across so many disciplines with millions being published every year that nobody can possibly keep up with them. And I find it very disconcerting that when I go to a doctor, I realize that he or she does not know the latest studies on my particular condition, even if they're a specialist. They just cannot keep up. And as computer scientists, I think we have trouble keeping up as well. So Da Vinci is the idea to apply our prowess in analyzing text, but not just to textbooks, also to hundreds of millions of scientific papers and see what we can get out, not as, you know, my doctor is going to be highly automated, but can we build a tool that helps doctors make sense of what's going on as a first step and ultimately suggest to them ideas and correlations and insights. So here's where we start, right? Today, if I ask you to read, find papers on information extraction, you go to Google Scholar, you'll see that you get 139,000 results, right? And even the top paper, great paper by McClellan, is from the year 2000. And you say, well, okay, I'll read that paper, but it's been cited by 1,100 other papers. Which one of them should I read? Well, I can click on cited by, and I'll find that each of these 1,100 papers were cited by a bunch of other papers. And again, the citation closure of this paper is enormous. And at this point, I more often than not give up and only read a very small fraction of what's available out there. That's a huge problem. So the approach that we're taking is we're building something called Semantic Scholar, where the idea is to help combat information overload. And the basic idea is we apply the same kind of extraction techniques I described to get from the paper the basic facts that are in there. We build a semantic index that then allows us to formulate much higher level queries, hopefully drill down much better into it. By the way, we're not just doing this over the text. We're working with Ali and a team from here, including Noah Siegel, who's a fantastic student that Anna recommended to me, and to actually extract the diagrams. And we want to do, we want to reach the point where we can ask queries like, show me a paper where collapsed Gibbs sampling does 10% than any other method, and it'll give you a list of papers based on the diagrams, and when you click on a paper, it'll pop up the diagram to show you that's what my answer is based on, and then you can click to read the paper. So not just text analysis, also vision. Here's our UI, and again, in the interest of time, we actually have a demo of this, but I won't show you the details. But the idea is to really develop much higher level of interaction with the papers. Okay, not just okay, I've got some keywords, here's the paper, or I've got some keywords, here's a subset of the paper. But here, for example, and this is something that's not yet operational, but we're aiming for. You type in information extraction. It gives you a progression of results in the field. Here's the percentages of success, and you can choose a particular technique and drill down further into it. So this is analogous, if those of you have seen Daphne Shachav's work on metro maps and so on. We're starting to think about how to create much more powerful visualizations and ways to dig into an enormous amount of information, because we have to. And to be continued. Anyway, I'm going to skip these examples because there's one more point that I want to get to, and I want to leave a bit of time for questions. So what are the common themes in what I've talked about? Hopefully I've convinced you that we're ambitious. We're also highly open and collaborative. We don't put IP constraints on anything you do at AI2 if you come there as an intern. And several people have, or if you work with us collaboratively. We're not trying to own this stuff. We're trying to enable the science. We're a nonprofit. We do emphasize, despite these very ambitious projects, having measurable results in the short term so that we're not just whistling Dixie. And we are leveraging the advances in big data. We're using machine learning techniques at the root of all these things, the machine vision work, the information extraction NLP work. But we don't just stop at simple classification. We use that as a building block to move further. The big data stuff is a brick. It's not the entire cathedral. And the result of that is these text mining systems that are starting to yield knowledge and reasoning and explanation. So that's what we're doing at AI2. The one last point that I wanted to make, and this is really something that's come up in, well, it's been going on for a while, but in recent days it's hit a fever pitch with Stephen Hawking's interview at NPR and Elon Musk's repeated attempts to bait me personally into responding. He couldn't care less what I think. But so what's wild is that there are radical misperceptions of AI by people who are very smart and very well-known people. So this quote, AI on the horizon looks like Amazon Web Services, cheap, reliable, industrial grade. Basically, Kevin Kelly, who was the founder of Wired Magazine, says in the near future, AI is going to look like electricity, like a utility. You'll just plug something into the wall, and AI would just flow out. It'll just, from the wall, you'll take the AI and you do stuff with it. Pretty optimistic statement. Elon Musk says the opposite, or actually maybe it's this another side of the same coin. He's saying with artificial intelligence, we're summoning the demon. I take this personally, right? I've been working in this field for many years, and I really don't think that I'm summoning the demon, but trying to build a program that can figure out how to pass a 4th grade test or how to understand a sentence. But, Mr. Tesla thinks that I am. So here's what I think the reality of AI is, and Dieter Fox can correct me on the state of the art here, but we're still in the very early stages of this field. Okay, there's a lot of really hard problems, and that's the reality. The other reality is, and this is from Jeff Hammerbacher, who was an early employee at Facebook. He left it to found Coursera, co-founded Coursera, and then he left that to be a data scientist at Mount Sinai Hospital in New York. He says that the best minds of my generation are thinking about how to make people click ads, right? In this kind of targeting, you're more likely to click on this ad rather than this ad. You're more likely to buy this product rather than that product. That is a huge focus on AI in companies like Google and Facebook and so on. And he said the best minds of my generation are doing this, and that sucks. Right? So that's the other reality of AI, is it's being used for, not the most highest and best use in my opinion. And so AI2's focus is to do AI research for the common good, whether it's Semantic Scholar or other projects, to do it to solve the problems that we really want solving, not to do it to get people to click on ads. And with that, I should acknowledge that any errors in what I said, any inaccuracies, any bold and ridiculous statements, there should be blamed on the AI2 team, and anything I said that has merit, that's really me. Thank you very much.
Are computers fast enough, or they're going to get fast enough for you to do what you want? I mean, are computers getting faster, better, fast enough for you to do what you want in a reasonable time frame?
So that's a great question, and we've so again, to repeat the questions, are computers fast enough to do the kind of computations we need for AI? Moore's law has been a huge benefit for AI. It turns out, though, that I think AI, and this here I'm quoting Herb Simon, is the study of ill-formed problems. Whenever we've been able to take an AI problem and formalize it precisely as an optimization problem or as a p-space complete problem, the brilliant people in this room and in other rooms have been able to figure out, even if it's whatever p-space complete or semi-decidable approximation algorithms, heuristic methods to get at the answer. So for the kind of problems that we're talking about, for example, taking information in the text, like people breathe air, and formalizing it appropriately, Moore's law and the amount of computation is not the bottleneck. The bottleneck is to figure out what's the right way to do it.
It's not right now, but is it going to be, especially at the scale that you're talking about? So.
If I were working on architecture, I would also really want the increasing computation to be important. And increasing computation is very important, Luis. No, absolutely. Yes, Linda.
In 1972, I really liked AI because my instructor was fun, kind of like you, and I set out to try to understand apples. I'm not kidding. And I wanted to try to describe an apple to a computer, and I couldn't figure it out, so I ended up in computer vision. I'm thinking that computer vision, it shouldn't be used just for understanding diagrams in text that you're reading. It should be used for everything that you need to understand. You need computer vision to understand all of the knowledge that you want to acquire. Is that not true?
So the question is, Linda studied AI in 1972. She didn't like it. She went into machine vision, and now she thinks machine vision is the be-all and end-all. Is that not true? Is tacked on at the end to make this seem like a question? And the answer is, it's not true. We have room for other techniques other than machine vision. For example, we have architecture. That's important.
You talked earlier about Mitchell's never-ending language learning project, and compared to that a little bit. And yet, there doesn't seem to be this never-ending learning aspect in any of AI2's projects. I'm wondering if you think that the never-ending learning is really an essential part of AI, and if you do, let me ask you back about never-ending language learning, because it seems like that was actually a failure. It stopped learning. Tom's moved on to another project now. Are there lessons about why it stopped and how AI2 would make a never-ending language learner?
That's a really fantastic question, and involves both specific questions about whether we're using never-ending language learning, and then more strategic questions about where to go in that direction of research. On the strategic questions where to go, I will defer to members of our scientific advisory board. To answer your question, I actually think there's an interesting point to be made here. the notion of building systems that are recursive and never ending and don't just learn in one shot but continue recursively is absolutely fascinating and necessary. We don't necessarily have any great ideas right now about how to do that. However, here's one of the things that we emphasize at AI2, which is to do empirical computer science research fast, we need to build on very strong engineering. So at AI2, we mix researchers and engineers working shoulder to shoulder, and we put a lot of effort into building systems that are easily reproducible and easy to experiment with. And we started out, we were doing an experiment a week. Now we're doing tens of experiments per day as we iterate through various parameters and various design decisions. It turns out that never-ending systems, like you described, do require a lot more effort to do that kind of experimentation. So I would say that the biggest reason that we haven't designed that interesting element into our system is that we're trying to build things that are really easy to work with. And having reproducibility, having simple paths to problems really helps us.
Okay. I'm wondering about your success metric. So you have this standardized test that fourth graders presumably perform, passing on at least. And your goal is eventually to match their performance. And also, say someone comes along and instead of doing this sort of smart, strong AI, understand what the language is, they just throw some language model, recurrent neural network at it, and get better performance than fourth graders, better performance than what you're getting. In your mind, is your goal to be the best computer system, or is your goal just to be human level performance but using sort of sound theoretical principles?
So, fantastic question. The question is, we have a benchmark task and we have these lofty goals. What's our real goal? Is it to pass the benchmark task, or is it to do fundamental research? And maybe there's a simple way to trick, simple tricks, cheap tricks could solve the problem. And in fact, with Watson, people argued about this. They said, well, Google can do this, or I can answer most of the questions using titles of Wikipedia pages, etc. And by the way, that's a big reason why we, in addition to science, we chose arithmetic and geometry as complements for Aristo. Because if you look at the geometry problems, I showed you an example, no way can Google do that, right? It doesn't understand the diagram, the language is not all what's in there. If you look at arithmetic problems, they're simple story problems like Joey had 23 pens, he gave 8 to Susie, how many pens does he have left, right? And the answers are 4 numbers. So those are particularly designed so that shallow bag of words technique can't solve this. You need at least to have some level of semantics. So my answer to your question is I think that we can have our cake and eat it too, in the sense that the questions are designed such that you need algorithmic advances in AI and AI methods to solve them. That's our hypothesis. We'll find out. But again, we're not assuming that. We believe that, but we're putting the data sets out there, and I challenge anybody to solve them better.
People are trying to do AI by building brain-like models of things. I'm an outsider. This was in some trade publication or something. And I remember thinking, the real limiting factor in the quality of the AI stuff that we can do is our impoverished understanding of the physical aspects of the brain and how that relates to cognition. Is that true? Is that discredited?
So the question is it really the case that the limiting factor of our understanding of intelligence, understanding the physical basis of the brain? When I was young and starting into AI, I would go up there and I would shake you by your shoulders and I would sit you for hours and persuade you of the folly of your ways. Now that I'm older and wiser, I'll tell you that there's multiple hypotheses, and the one that I'm working under could actually be wrong, shocking as it is. So there's the Allen Institute of Brain Science, and more broadly, a huge amount of exciting effort on neuroscience. And that may well turn out to be a better way to figure out intelligence. We're taking different approaches. So far, the work on the physical basis of the brain has not emerged to have very high-level conclusions, okay? So they found the neurons are fascinating. They found all kinds of localized phenomena in the brain. They haven't generated functional insights that we could use in the design of computer programs to make them better intelligence. That doesn't mean that they're wrong. It just means that they're not winning the race right now. We have our own challenges, as I alluded to. So I would say now in my older, wiser stage, the jury is still out, and there's a t-shirt waiting for you down here if you want it. Thank you all so much. It's a real pleasure.
Thanks, Oren.